So section 4.2 is going to discuss some of the applications of our exponential function. At the end of section 4.1, we kind of derived the existence of this nice new constant e. And now we're going to use this in various applications, one of which is kind of a fun one, which is our compound interest formula. Continuously compounded interest is given by this formula, a equals p e to the rt. The formula itself will be given to you on the exam. How to use it and where to use it will not. But in problem 34, they asked us to invest $3,500. So P equals 3,500 at an interest rate of 6.25%, compounded continuously, which means you're going to use this formula. If it was compounded like n times a year, then you'd be using this formula, 1 P times 1 plus R over n to the nt. So both formulas will be given to you. You need to know which one to use where. But if it's compounded continuously, that's when you use this formula right here. So in problem 34, they want us to figure out, well, how much money is this going to be worth at this interest rate after 3 years, after 6 years, and after 9 years. Now, there's a couple different ways you can get at this, but let me show you my bias towards doing this one. Let's first of all plug in this information. 6.25% needs to be changed. We need to write it as a decimal. So what is it as a decimal? Good, thank you. 0.0625. All right, so make sure you shift the decimal 2 places to the left. And from there, I'm going to plug it into this formula. So A equals 3,500 times e to the 0.0625 times time, which is just going to be a t, or an x is what we'll use when we put it into our graphing calculator. So let me put that into my graphing calculator. And let's see here. There we go. 3,500 e to the 0.0625 times x. Just using x as opposed to a t because it's not very convenient to use t in this case. When you get that set, press the second key, then the graph key to take us to the tables, and we can just type in whatever we want. So we can type in a 3 and get like 4,221 something dollars worth after 3 years. After 6 years, it's a little over 5,000, and after 9 years, 6,142. But there's one thing that's missing from all this. If you're making a little table of these values, and that is, I need to know the decimals here. Where do you round your money calculations to? To what digit? Hundredth. And I'm not getting the nearest hundredth out of this. When I look at this, I'm getting it round to the nearest tenth. But if you actually put the cursor on these numbers, then on the bottom row of your calculator, you'll get all the decimals that you need. So the first one will round to 4221.81. The second one will round to 5092.47. And the last one is going to round to 6142.69. Now you don't have to do it with a table. I just found it convenient just to have to enter this expression once. and then just type in the numbers 3 different times. Here's kind of an interesting one, though. What if I invested my money for, say, 11.09 years? Now, hardly an arbitrary guess on my point, but look at how much money you've got. What would that round to? It's about how much? About 7,000, right? Which is twice as much as what you started out with, right? So 11.09 years is what's called the doubling time. That's how long it takes your money to double. So it's of interest to know that. And later on in Chapter 4, we'll learn how to find that number, your doubling time. For now, though, let's concentrate on E a little bit more. E, like we said, was about 2.71828. You can find E right above the division sign on your calculator, right here. And with that knowledge there of E, I want us to think about this for a second. What's a graph of e to the x going to look like? So y equals e to the x. Well, that's an exponential function. There was 3 things that were present in that graph that I said you should expect. Do you remember what those 3 things are? You can look back at your handout. It grows quickly. Good. What else? Passes through 0, 1. Don't make one person do all of it for you. What's the last one? All right, it's got a fixed base, which is your 2.718. But what was the last thing that was true about the graph there? Thank you. It gets close to, but never quite touches the x-axis. So here's 2 exponential functions. Y equals e to the x, y equals 2 to the x. They're pretty close, but try and decide which one's which. Try and decide which one's the graph of the exponential e to the x, and try and figure out, well, which one's the graph of 2 to the x. See if you can't figure out which one's which. And if not, at least take a guess, right? You got a 50-50 chance. So what do you think? Which one's this one? E to the x. Now you can see it this way. At x equal 1, 2 to the 1 is 2. And e to the first power is going to be about 2.718, etc., but it's certainly going to be bigger than 2. So what you see is that the size of the base, by increasing from 2 to e, you're going to have a taller graph. So this one's your graph of e to the x. And that's going to continue over here like that. And the smaller of these is going to be 2 to the x. Now, it's smaller to the right of the y-axis. It's actually taller to the left of the y-axis. But the important thing to see here is that it still has the same basic 3 characteristics, and we can still shift it around much in the same way that we did with problems in section 4.1. Now, let's do a little bit of that. Do a little bit of shifting for a couple problems. Problem number 8, for instance. H of x is e to the negative x minus 3. So you're going to take your basic graph of e to the x. How are you going to change that graph? How's it going to be shifted? All right, so there's 2 changes. And Courtney nailed it pretty good. Actually, very good. This is going to flip around the y-axis. Flipped around the y-axis. And then shifted down by 3. So both of those changes will be made to your graph of e to the x. So really, in this new graph, you'd have something that kind of faces down like that. And the one point that I care about, the point at 0, 1, in the old graph would actually be at 0, -4 in the new graph. Let's try a different one like that. Problem number 12. 12 is kind of interesting. F of x is negative e to the negative x. A couple things going on here. See if you can't figure out what's going on with this one. So what's going on with this one? What's the negative out front do? Yeah, this one flips it around the x-axis. Flipped around the x-axis. And how about the other one? Yeah, it'd be a decreasing function in the third and fourth quadrants around the y-axis. So let's actually graph that one, just for giggles, just to see what it looks like. You can do it on your graphing calculator. I think I want to just do it briefly up here on Desmos. It's just so easy. So Desmos, y equals negative e raised to the negative, try it again. Y equals negative e raised to the negative x. So yeah, pretty much like we expected. Let's take a look at the graph of y equals e to the x in comparison. E raised to the x. Yes. So let me get rid of these real quick. No, this is actually an increasing function, right? Because you move from left to right. Well, as you move from left to right, the function is getting taller. So that makes it an increasing function, right? The y-coordinate is increasing. So when I move in this direction from left to right, take a look at the y-coordinates. They're getting bigger. So it's an increasing function. What? Well, it's still an increasing function. Even though it's negative, it's still getting bigger. It's just not as negative. So there's your graph originally. Then we flipped it around the y-axis. And then we took that one and flipped it around the x-axis. So those are the different shifts involved in this graph. But yeah, it's an increasing function. Appreciate the question on that, though. Let's work with problem number 28. Let me put that one up here for us. And this reflects the population of birds. So problem 28. And gives us our population, calls it n of t. So the number of birds is a function of time, n of t, like this. 5,600 divided by 0.5 plus 27.5 times e to the negative 0.044t. Now it's going to ask us for a couple things on this one. I would suggest we put this into our calculator, and we're going to look at it on our calculator and see what happens. Now, when you put it into your calculator, I think the easiest way to do this is to take advantage of some of the tricks that you can do on your calculator. And that is, let me clear this out. hit the alpha key, then the y equals key. That gives you a menu that allows you to put in different fractions. And choose the first option there, so that you got a numerator and denominator. You don't have to worry about as many parentheses. In the numerator, it's going to be 5,600. In the denominator, it's going to be 0.5 plus 27.5 second ln e to the negative 0.044x. So you should be able to put in something like that. Now, if you don't have capabilities to do that, or you just forget where that is, you can put it in, but it's going to require a lot of parentheses. It's going to require a parenthesis around the entire denominator, parentheses here for the exponent. It becomes kind of a pain. So, yeah. So everyone got that programmed in? So once again, on the numerator-denominator stuff, to get that, you'd hit the alpha key, then the y equals key, and it gives you 4 different options. The one you want for a numerator and denominator is the first one, and that'll allow you to do fractions like 7/8 or whatever you need to type in. All right, once we have that there, let's take a look at the questions that they asked. So, first question they ask in this is, what's the initial population? So, here's the question itself. Certain species of birds is limited by the type of habitat required for nesting. Population behaves according to the logistic growth model. Here, find the initial population. Well, it's going to mean plugging in some value for t. What value for t would represent the initial population? T equals what? 0. Yeah. T equals 0. At time 0, that's what you're starting out with, right? So the easiest thing to do, especially since we've got this already programmed into our calculator, is to go to the table and delete all these old values with the delete key up here. Delete, delete, delete. And type in a 0. You should get a nice even 200 out of this. If you don't get a nice even 200, you put in your function in the wrong way. So that's our initial population. T equals 0. N of 0 is 200. So 200 birds initially. But what tends to happen with populations? Yeah, they tend to increase, right? So the question then in part B is to graph this. So let me make some suggestions for our window. So for x minimum is 0. We don't want to look backwards in time. So we're going to look forwards. So 0 to, let's go up to 500. And I'll be very honest with you, I had to play with this to get these things right. Let's put a scale of 100. On the y-axis, minimum of 0. If our population reached 0, what would that say about the poor birds? They're extinct, yeah. Hopefully that won't happen to it. But we'll start at 0, and we'll go up to 12,000. Now, hopefully you don't leave y scale as 1, because your calculator is going to really work hard to try and get 12,000 tick marks up and down here. So let's make that something a little bit bigger, like 1,000. And then hit the graph key. And what you'll see is that the population takes off for a while, but not forever. What happens after a while with this population? Yeah, it levels off, right? So this is the graph, and last little bit is it leveling off. So the question is, where does it level off? What is it leveling off to? Well, you can kind of estimate roughly where it is, but we don't necessarily have to estimate roughly where it is. Hit the trace key. It puts a cursor on your graph. And then use the arrow key and move to the right. And take a look at the y coordinates. So you see the y-coordinate down here. What's that y-coordinate getting close to if you rounded it off? What's it getting close to? Not 12,000, because that's the top of this. 11,000 what? About 11,200. So that's kind of like the limit here. So approximately 11,200. That's the limit of this population. It's like, okay, they've used all their nesting territory. They're not going to get any bigger. That's what's going on there. Yeah, you want to get your room to stretch while you still got it, huh? Well, speaking of room to stretch, a very simplistic growth model for populations would be the same thing as we have for compound interest. So let's see. Earth population. How many people are there on this planet, roughly speaking? Higher, a little bit higher. So our initial population is from today is about 7.7 billion. When I first started teaching this class in 19 mumble, we changed over. We reached the 6 billion mark. It just stuns me that we've added, over 1.7 billion people since I first started teaching this class. That's a lot. Yeah. Well, yeah. India. I mean, if you're unique, a lot of times they say you're 1 in a million, right? If you're 1 in a million in India, there's 1,300 people just like you. Yeah, that's just crazy. So now our current growth rate has been slowing down, but their growth rate is about 1.07%. That's I think 2017 numbers. So if we take kind of a simple model approach to this, like our compound interest, A equals 7.7 times e to the 0.0107 times t. So that's going to model our population growth, in the near future. Now, it probably won't last this way forever. It can't. At some point, we're going to run out of resources. We're not going to be able to sustain this kind of a growth rate forever, at least not with our current way of doing things. So let's just play around, though, and make a prediction. What's this going to be like 10 years, 20 years, 30 years, 40 years? What do you want? When you retire? Let's take a look at things when you retire. 40 years from now, when you retire. So let's let t equal 40, or whatever number you want. You don't have to follow along. But let's just practice this. 7.7 e 0.0107 times 40. So in 40 years, wow, almost 12 billion people now. That's why Demetrius is stretching now. He's like, yeah, I got some space now. I want to use it while I can before it gets too crowded. Yeah, it's going to get crowded. Buy up your lakefront property now. I plan to be here in 40 years. Heck, I haven't hit my midlife crisis yet. All right. How are we looking here? All right. Now, there's other examples in this section of the exponential function. That was just one of many. Kind of a fun one that's going to be in your homework is skydiving. What you're going to see is that after a while, you reach a limiting speed. There's only so fast you can go falling down, then enough air resistance is going to keep you from going any faster. So, let's see. There's one last one that I wanted to do here. No, I have not gone skydiving. My mother asked me if I was ever stupid enough to go skydiving, not to tell her. She goes, even if you survive, I don't want to know. So I'm like, okay. So no, I've never gone skydiving. It looks fun. It looks a lot of fun. No, the only air I caught is coming off a mogul while skiing. Yes. Oh, yeah, those gliding suits. Yeah, yeah, those. That's pretty cool because what you can do is you can slow down your rate of descent. So it really extends your time in the air if you have one of those wingsuits. And basically, you can move 3 feet horizontally for every foot you lose vertically, I think is the ratio. So you can really stretch out your time in the air if you're wearing one of those suits. It looks crazy, and a lot of those people start making sense. I don't think you're going to be flapping on those things. Do you want any more practice with exponential functions, or are we good there? We're good? Okay, cool. Let me give you some homework then. For homework, try 5 through. Let's see, is that right, or is that this isn't the last section? Is it? No, 5 through 13, then 23 through 27, 33, and 35.